All right, students, welcome back for the second part of the lecture series on nuclear chemistry. What we're going to start to talk about this time is the energies associated with nuclear reactions. So up until now, um, energy generation by nuclear reactions and nuclear power plants have operated off of nuclear fission, which means larger nuclei breaking apart into smaller nuclei and in the process releasing energy. An example of a fuel for these nuclear reactors here would be uranium-235. So if uranium-235 is struck by an electron, that can start a neutron, that can start a chain reaction in which it breaks apart into two smaller nuclei and releases several more electrons, which then go on to hit more of the uranium, the uranium-235, and those break apart, and you get a kind of runaway nuclear reaction that generates a lot of energy. And this is the reason why nuclear fission, nuclear power plants that exist in the past have the danger of having an out-of-control reaction that produces too much energy and destroys the reactor and releases the radiation into the environment. Now, modern nuclear reactors have a lot of fail-safes to ensure that doesn't happen. So nuclear is actually, and even nuclear fission is a very good, solid, clean energy choice these days, even though a lot of people don't support it. I think most scientists who understand nuclear fission these days would be in support of more nuclear energy as opposed to combustion. The amount of energy that is made is described by this equation, E equals mc squared. You've probably heard of that in association with Einstein, who is the one that developed the equation. He sure had a great way of producing very simple equations for a great variety of things, this one being very simple and beautiful. It describes the relationship between mass and energy. So we think in the past, we've always thought about the law of conservation of mass, that in chemical reactions, mass can neither be created nor destroyed. But in reality, small amounts of mass are created and destroyed, especially in nuclear reactions. And the mass that is lost in these nuclear reactions has an equivalent energy to it. And so we can calculate what that energy would be. This is a diagram of how a nuclear fission reactor works. There's going to be basically a place here where the fuel elements are. That's the uranium. This is the reactor. And this is where the nuclear reaction takes place. It's in contact with water, and that water is heated by the nuclear reaction. But then from then on, the rest of the reactor is the same as any other electrical generation reactor. Heat is used to boil water, which produces steam, which turns a turbine, which is a large fan connected to a copper coil that turns within a magnet, and this produces electrical energy. That water is then condensed and reused. And so the part about a nuclear reactor that's different is this part right here, where a nuclear reaction is occurring in contact with the water. Now, nuclear fission is different from nuclear fusion. So I was discussing at the beginning of the last lecture this cool new ITER reactor that we're hoping to get sustainable nuclear fusion from. So all of the energy that we enjoy, even from the fossil fuels that we burn, this all came originally from the sun. And the sun produces energy by the process of nuclear fusion. The sun is mostly hydrogen. Its hydrogen atoms are moving very, very fast because they're in the middle of the sun and they're very hot. And they crash into each other and they sometimes fuse and they produce a heavier hydrogen atom, hydrogen 2, and a positron. And those heavy hydrogen atoms, these are even more likely to crash and fuse with another hydrogen atom, a hydrogen 1, and this will produce helium, and then these can go on. The remaining reactions actually produce helium and other larger elements. So all of the atoms that we're made of, for example, which are larger than helium, those were born in the heart of stars with these fusion reactions happening. which is really interesting. It's really interesting that all the atoms that make us up and the world, the Earth that we live on, came from these types of fusion reactions that happen inside of stars. You don't need to memorize this or anything. The main point is nuclear fusion is the opposite of nuclear fission. It's the joining together of lighter nuclei. So the question is, if we're doing a fusion reaction, one interesting question is, how much energy would be released by this fusion reaction, like the one that happens in the sun? So an example fusion reaction is shown here. It's got two hydrogen-2 nuclei coming together to make a helium-3 nucleus and a neutron. This is an example of one fusion reaction. And the question asks, how much energy would be produced when this happens? Well, what we need to do is we need to know what was the mass that was lost in this process. We're going to use E equals mc squared here. Okay, so we've got masses here of the hydrogen-2 nuclei. They're 2.0141 AMUs. And we've got the mass of the helium nucleus 3.0160 AMU. And we have the mass of the neutron, 1.00866 AMU. And we have to be very precise about these because the difference in mass is going to be really, really small. Even an AMU is really small. So this is what an AMU is in grams. And so what we want to do here is we want to figure out how much energy was lost. And we're going to start by figuring that in AMUs. So we start with two of these. So we want the change in the mass, or delta, this triangle delta indicating change. We want change in mass. So this change in mass is going to be what we start with, 2 times 2.0141 AMUs minus what we end with. So we're going to say minus 1 times 3.0160 AMUs plus 1 times 1.00866 AMUs. Okay, and so we're essentially subtracting both of these. So let's do that calculation. So we get oh no. So we get 2. Oops, I've got it off the screen here. Okay. 2 times 2.0141 minus 3.016, and we're also subtracting this because we distribute the negative. So minus 1.00866 equals, and our amount of mass lost was 0.00354 AMU. So delta mass equals 0.00354 AMU. 0.00354 AMUs. Now, one important fact about using E equals mc squared is that we need to use the SI, the metric unit for mass, which actually is not grams, it is kilograms. And so that's the biggest mistake that people usually make when doing this kind of problem, is they use grams instead of kilograms. You're going to have to use grams, and I'll show you a little bit more about why. But we're going to have to use kilograms. But let's convert AMUs to kilograms. So 1 AMU is 1.66054 times 10 to the minus 24 grams. And we're going to convert this to kilograms. So 1,000 grams is 1 kilogram. And our AMUs cancel here. Our grams cancel, and we should have kilograms. Okay, so our change of mass in kilograms now is going to be, calculate it, 0.00354 times 1.66054 EE negative 24, and then divide by 1,000. So we're talking about a tiny mass here, right? Okay. So this is 5.87. I'll just do 366. 878. One more. 878 times 10 to the minus 30 kilograms. Now this is for one helium 3. This was asked for a mole of helium 3. So we're going to, so this is, I'll say, per helium 3. And so we're going to have to multiply times 6.022 times 10 to the 23rd helium 3s to get the actual mass. Okay, so that will be the mass for a whole mole of them. So times 6.022 EE23. And now we get, I'm going to change this to scientific notation, we get that the change in mass was 3.54 times 10 to the negative 6 kilograms. Okay. Let me make sure that I got the same amount on my next slide. Yeah. Oh yeah. Okay. Oh, I did it the other way around first. Okay. The other thing we could do is, remember this one here, I'll just continue with what I wrote here. This is what we did at first, and we had this many kilograms for one helium 3, right? And now we can apply E equals mc squared though. And here's what's really important. E equals mc squared. The mass has to be in kilograms, okay? And this is the value of c. C is the speed of light. So its value is about 3 times 10 to the 8th meters per second. It's the same every time. And we square that. Okay, so let's punch this into the calculator now. I'm going to square this first. So 2.998 EE8 squared, and then I'm going to multiply times this, times 5.8799. I carried a few digits there compared to my previous calculation. EE negative 30. Let's see, 5.29. I got something a little bit different. It's close enough. So let's just 5.2. Okay, 5.3 times 10 to the minus 13. Now the unit here is joule, and let me explain why. The unit that you get here, just let's analyze the units real quick. We have kilograms here. Oops. Kilograms. And then here we have meters per second squared. So that's going to be times meters squared over seconds squared. So you have kilograms, meters squared, kilograms, meters squared per second squared. That is what a joule is, okay? If you take more physics and chemistry, that's going to get ground into your brain. A joule is a kilogram meter squared per second squared. It's a Newton meter, in other words. A Newton is a kilogram meter per second squared. Newton is a measurement of force, and energy is force times distance. So when you take more physics, if you're taking physics, maybe you've already encountered that. That is why your mass must be in kilograms, okay? And this is going to be generally true. When you are doing these types of calculations where you're going to get a different unit, the SI derived units, that's what they call a unit like joule, will always have kilogram as the mass, not gram, because kilogram is actually officially the base SI unit, not gram. I guess because gram is so small. So this is for 1 helium nucleus. We want this per mole. So we got to take this and multiply by how many a mole would be. We do 5. And I know my number was a little bit different, but let's just say 5.3, close enough. I'm not sure what happened with the punching there, but it was close enough for me. And so we want joules per mole of helium. So if we multiply like this, our helium 3s cancel, and we get joules per mole of helium 3. Okay. So now 5.29, I'll say, times 6.02 E23. Or get, is this what I got? 3.18, close enough, times 10 to the minus 11, no, positive 11, sorry about that. Boy, I've got a few mistakes here to clean up. To the positive 11, there we go. So as you can see, a mole of helium isn't that much. So a mole of helium is like, 4 grams. But if you do fusion with 4 grams of helium, you get tons and tons of energy. This is the promise of nuclear fusion. A huge amount of energy, so huge, from so little material. And so that's why, I'm so excited about ITER, right? So ITER is going to be a really big deal. If we can get nuclear fusion going, we get giant amounts of energy off of very little mass. So that's pretty cool, right? I'm sorry there was a little bit of off with the calculations there. I'll have to double check my punching, but it was close enough that it didn't matter. 5.3, 3.2, we got the same ultimate result to 2 sig figs, so that's good. Okay. So this is how much is produced, how much energy is produced with nuclear fusion. We use E equals mc squared. Now, using E equals mc squared all the time can be a bit cumbersome. We're going to be using it for another purpose too. It is to calculate the nuclear binding energy. So another reason why the nucleus sticks together is because the mass of the nucleus itself is less than the mass of the separate nucleons, which are protons and neutrons. Okay, so nucleons is a word for protons or neutrons, either one. So what happens is when these nucleons come together, they lose some mass, and that contributes to the energy that binds them together. So the mass that's lost is released as energy, according to E equals mc squared. So we'd have to put that energy back in to break the nucleus back into its individual protons and neutrons. So that's the definition of nuclear binding energy. It's the energy that you would have to put into a nucleus to break it into 1 mole of the nuclei into their individual nucleons or protons and neutrons. Generally, the binding energy is expressed using a unit called electron volt, which is the charge required to pull an electron away from a volt of current, a volt of potential, electrical potential. We'll talk more about volts when we get to the very end of the class. So if you take the nucleus, you put in the binding energy, you'll separate the nucleus into its nucleons. Now, instead of using E equals mc squared, there is a shortcut. This is a big, very nice shortcut, and you can always use this. Of course, it's maybe something you want to put in your notes for the exam. I'll give it to you on the reference page as well for the exams. But 1 AMU, if you do E equals mc squared on 1 AMU, it is equal to 931.5 times 10 to the 6 electron volts, or also known as 931.5 mega electron volts. Mega means a million, so this is a million right here. Often your binding energy you'll want to calculate in terms of mega electron volts. So this gives you a very nice shortcut that lets you work around E equals mc squared. Let me show you why it works here. So use E equals mc squared and the definition of an AMU and an electron volt. So an electron volt is in joules is 1.602 times 10 to the minus 19 joules. Use this to show that 1 AMU, when converted to energy, is 931.5 mega electron volts of energy. Okay, so what we're going to do is we're going to use E equals mc squared here. The plan is we're going to turn AMUs to kilograms. We're going to plug them into E equals mc squared and get the number of joules. Then we're going to convert the joules to electron volts. Then we're going to convert the electron volts to mega electron volts. So step 1, take the AMUs, convert them to kilograms. So 1 AMU is 1.661 times 10 to the minus 24 grams. So 1 AMU is what we start with. 1 AMU is 1.661 times 10 to the minus 24 grams. So our AMUs cancel here. So we put AMU on the bottom. AMUs cancel. We get grams here. Grams. And then we turn grams to kilograms. 1,000 grams is 1 kilogram. So we get kilograms. Okay, so we can punch that in our calculator. 1.661 EE24, make that negative, divide by 1,000. We already did this previously, so we got 1.661 times 10 to the minus 27. Okay. Now we want to convert, we want to use E equals mc squared. We're going to plug this into E equals mc squared. And we're going to get the number of joules that this is. So E equals mc squared. We put our 1.661 times 10 to the minus 27 kilograms here, and we put in the value of C. C is about 3 times 10 to the 8th meters per second. And we punch that out in our calculator, so we have this times 2.998, and I encourage you to do this with me and make sure you can do it, times 10 to the 8th squared equals, and we get 1.493 times 10 to the minus 10, and the units are kilograms times meters squared over second squared, or to second to the minus 2 power, which is joules. So next we want to convert joules to electron volts. Okay, I'm going to write this on the side, but it's going to show up underneath too. All right, and we'll do, and so that's the relationship here. 1.602 times 10 to the minus 19 joules is 1 electron volt. That will get us electron volts. And then to get mega electron volts, we're going to multiply times, so 10 to the 6th, or a million electron volts, is 1 mega electron volt. And so let's do that now. So I should retype this. That's probably why I got a little bit different answer, is because I didn't round it in the middle. So a little bit of rounding difference can make a big difference in calculations like this. Okay, so then we're gonna divide by 1.602 EE19, make that negative, and then divide by 10 to the 6th. So 1 EE6 equals, and we get 931.9. That's what I got here too, 931.9, and almost 932. A little bit different than 931.5, probably just due to rounding errors, but close enough. Okay, so this shows you that you can use this relationship. 1 AMU, you can convert that directly to the energy value of 931.5 mega electron volts. That way you can skip E equals mc squared entirely, which is pretty convenient. So I wanted to show you E equals mc squared a couple of times to make sure you could use it, but now you got a shortcut. You can go straight from AMUs to energies in mega electron volts. This is basically, this takes, what we've done is by getting this, we've taken all of this work and just turned it into a conversion factor, because this part of the work will always be the same. We'll convert however many AMUs to a number of mega electron volts. The only thing that will differ is how many AMUs, but then we can just use this conversion factor and our number of AMUs to convert to energy. So this is a nice little shortcut. So we've been talking about nuclear fusion and fission, but you may be wondering, why does this even happen at all? Like, we said that large elements tend to break down into smaller ones, like uranium-235. We showed that as an example of nuclear fission. That nucleus breaks apart into smaller nuclei. And then hydrogen in the sun undergoes nuclear fusion. How come some nuclear fusion processes can make energy, and also some nuclear fission processes can make energy? The reason why this is because the most stable elements, this most stable nuclei with the lowest energies, are actually near the middle of the periodic table. The most stable nucleus that we know of is iron-56. So this is the lowest in energy. It has the largest binding energy, so it's the hardest to break apart as well. So as the universe continues to go on, all atoms are actually eventually going to fuse or undergo fission until they become iron-56. The end of the universe is a bunch of iron-56 atoms. And you can see here the difference between the energy produced by fusion of hydrogen and fission of uranium-2. So when uranium undergoes fission, it's creating, other elements that are slightly higher in binding energy. So up on this vertical axis is binding energy. These are more stable nuclei. So as nuclei that are larger than iron-56 undergo fission and get smaller, this releases energy. But this energy is actually pretty small. The energy difference is pretty small compared to the difference between hydrogen and other elements. When hydrogen fuses to helium, the binding energy difference is huge. So a huge amount of energy is released when hydrogen fuses. And that's why nuclear fusion is so awesome. It's because for so little hydrogen we can get so much energy. It's even much better than doing nuclear fission. And the nuclear reactor can't run out of control, because the hard part of making nuclear fusion happen is actually keeping the reaction going and producing more energy than it takes for us to keep it at the high temperatures required to make it happen. So this nuclear binding energy, this is calculated in mega electron volts, and we can use the little shortcut that we have now to calculate this from the energy difference between the iron-56 or some other element and its individual nucleons. So iron-56 is the most stable nuclide. It's extremely stable. compute the binding energy per nucleon for iron 56 and compare it with that for carbon 12. So the mass of an iron 56 atom is this right here in AMUs. And remember, the binding energy means the energy it takes to take that iron atom and separate it into its individual protons and neutrons. And so this H1, which is a proton, because it has no neutrons, weighs 1.007825, and a neutron weighs 1.008665 AMUs. So our plan here is that we want to find the delta M, the difference in mass between the iron 56 here and its individual protons. Iron 56 has 26 protons because it's iron, and 30 neutrons, not 20. Oops. 30 neutrons. So we can calculate the mass difference between the nucleus itself and the individual nucleons, the protons and the neutrons, and that gives us the binding energy. Okay, so let's go ahead and do that, right? So what we want is we know the individual nucleons are going to weigh more, so we'll take those and subtract them. So we want the difference in the mass is going to be 26 times the mass of the neutron plus, or sorry, the mass of the proton plus 30 times the mass of the neutron minus the mass of the iron 56. Okay. So this is going to be 26 times the mass of the protons was 1.007825 AMUs plus 30 times the mass of the neutron, which was 1.008665 AMUs. And we're going to subtract from that 1 times the mass of the iron atom, 55.934939 AMUs. Okay. And I'm going to put that right here because I'm running out of space. So let's calculate that. So this is going to be 26 times 1.007825 minus 30 times 1.008665. Whoops, I did minus instead of plus. Damn it. Whoops, sorry. 26 times 1.007825 plus 30 times 1.008665 minus 1 times 55.934939 equals 0.528461. 528,461 AMUs. And I think these all go to 6 after the decimal, 6 after the decimal, 6 after the decimal, 6 after the decimal. So our last sig fig is the 1. Okay. Well, let's carry that forward now. Let's make sure I got the same. 528,461. Okay. And now what we're going to do is we're going to convert those AMUs to mega electron volts. And then we're going to divide by the number of nucleons because we want the mass per nucleon. So 0.5284461 AMUs. And we're going to use that handy dandy conversion factor that we got. That 1 AMU gives us, let's go back. What was it again? I don't have it memorized. You'll be able to have it for reference. It was, I lost it. There we go. 931.5 mega electron volts. 931.5 mega electron volts. Okay. So we'll get however many mega electron volts. So times 931.5. And of course, this is going to limit our sig figs, unfortunately. So we're kind of approximating here. So that is going to be 492.261 mega electron volts. And we only have 4 sig figs now because of the conversion factor we chose to use. And then finally, we're going to divide that by the number of nucleons, which is 56. So we're dividing by 56 here. So let's divide it by 56. Divide by 56, and we get 8.790 mega electron volts per nucleon. And so that is the binding energy here for iron. And so this, obviously, if we look back at that plot, we saw iron 56 was the most stable nucleus. Of course, it would take more energy to break a nucleon up than carbon 12. It's the most stable one. Okay. So that wraps up the second lecture, which is about nuclear energy, nuclear reactions and energy. In the last lecture, we're going to talk about nuclear transmutation, the speed of nuclear reactions, the kinetics as they call it, and some of the health effects of exposure to nuclear radiation. So I'll see you on the next video.